Hello students, welcome back. Previously, we went through some detailed explanations of the exponent rules, but that was an optional video, and a lot of students may have skipped because they felt comfortable with these rules. Nonetheless, let's skim through those as briefly as possible. Let a and b be positive real numbers, then they're going to be the basis, and let x and y be arbitrary real numbers, and they're going to be the exponents or powers. When x is 0, a to the 0 power is 1. Not 0, but 1. When x is 1, a to the first power is a itself. In other words, if there's nothing there, 1 is hidden. Negative first power is reciprocal, 1 over a. Negative x power, again the reciprocal, 1 over x power. Remember all those? Now let's go to the second line. A to the x power times a to the y power. We just add up the powers. A to the x power divided by a to the y power, we subtract the powers. Please remember the parallel. Multiplication, take the inverse, we have division. Addition of powers, take the inverse, we have subtraction of powers. So this and that are just inverse relations. Third rule, a to the x power to the y power is a to the xy power. We just multiply the powers. Now let's go to the line 3. If we have same powers and different bases, we just distribute the powers, either for multiplication or division. And repeat these rules, then you can do that for 3 bases, 4 bases, whatever. So much for exponent rules. Now let's go to exponential functions. And here's the definition. A to the x power when a is strictly greater than 0. That's the definition of an exponential function. And depending upon the a value, I'm going to get various different types of functions. I mean, they're all same type, exponential functions, but various different functions with different behaviors. Now, how do we define these for arbitrary real number x? Actually, that's very, very tricky issue, to tell the truth. Do you remember the optional video? If you went through, you'll remember. I didn't go through any of these for arbitrary real numbers. Even for rationals, I didn't. I restricted myself only for integer cases when we have repeated multiplication or division because those are easy to understand, otherwise too difficult. But we cannot run away from that forever. We have functions defined for real numbers, so we have to somehow establish it. How do we do that? Let's do our best. Let's start from rational numbers, starting from whole numbers and negative integers, and finally rational numbers, and then try to extend over to arbitrary real numbers. Now, when x is a whole number or negative integers, everybody should be able to understand easily. Now, for rational numbers, try to understand as much as possible. If you have to throw in a towel at some point, go ahead and do that, but you have to remember the end result in the end. Okay, that was an advanced warning, and let's begin. Okay, here's the easiest case. When x is a whole number, 0, 1, 2, 3, and so on, that's just a repeated multiplication, x times. X is 0 in that case, no multiplication, so we end up with this, a to the 0 power is 1. Now when x is 1, then multiply just once, so you get that, just a. In general, we have repeated multiplication x times. Now what if x is a negative integer? Then x is negative 1, negative 2, negative 3, or in other words, x is a capital X where capital X is 1, 2, 3, 4, positive. So we have 1 over a to the capital X, and capital X is positive, so we have repeated multiplication, except that happens denominator. Okay, here we go. When x is a whole number, repeated multiplication. When x is a negative integer, then we have repeated division. Those should be easy. Now, let's go to number 3, and this is going to be a huge headache for a lot of students. Try to follow. Okay, x is m over n in the lowest terms, and m can be either positive or negative, and denominator n, let's keep it as positive. Okay, when this whole thing is positive, then positive or positive, no problem. When the whole thing is negative, we'll assume m is negative and n as always positive integer. And then when m is positive, a to the m power is repeated multiplication, so no problem. When m is negative, then like this, repeated division. So this thing becomes repeated division. Again, no problem. So a to the m power is well defined. Basically, we define a to the m over n power as the nth radical of a to the m power. Looks like a little bit bigger font will be helpful here. So we define like this: a to the m over n power as the nth radical of a to the m power. And a to the m power is well defined, either repeated multiplication or to repeated division. Either way, it's okay. But then again, what do you mean by nth radical? It's this: y is nth radical of a to the m power is defined by y to the nth power is a to the m power, and both are positive. A is always positive. Yeah, we're going to consider only that. But also, y value, the function value, is also defined always positive. So that we only have one value, you see. And that's well defined, so we can extend this idea to rational numbers as well. Now, if you were able to follow all this for rational numbers, great. If you did not, well, that's okay, as long as you memorize this. A to the x power for whole numbers, repeated multiplication, no problem there. When x is a negative integer, repeated division, again, no problem there. Now finally, when x is a rational number, m over n, then you define it as nth radical of n power. The numerator becomes power, the denominator of power becomes radical. Just remember it as a formula. Now, in order to help you understanding, let me give you some visualization. I hope this will help you understand even better. Here, the program is randomized, so I ended up with a equals 1.577, and I plotted a to the x power, where x is a rational number, but there's so many rational numbers, and infinite many of them, so I selected only a few, n over 20, where the numerator is negative 100 to positive 100, which means 100 dots here in the left-hand side, and 100 dots here in the right-hand side. And then at y-axis is 1, so I have 201 dots here. And you see a lot of gaps, right? That's because I have only a small number of dots. Now, if I increase the number of dots, and I'm going to get more filling, and eventually if I complete them up by joining everything together as a smooth, continuous curve, then I'm going to get the exponential function a to the x power. That process, joining all those together into a continuous curve, that process is called completion, and I completed this graph. People call those kind of names. The term mathematicians use is completion. You can complete the graph to get y equals to a to the x power for arbitrary real numbers. So what is completion? Joining together all those together and make into a continuous curve. If you do that, you're going to get these kind of graphs. Please note that I don't have dots anymore. I have continuous curves. And here I have some special cases. A value is 3/2, 2, and 3 respectively in blue, red, and green. And then here's another example. A value is 2/3, 1/2, and 1/3 respectively. And we have blue, red, and green graphs. Let's see those together in the same viewing window. When a is greater than 1, we have this kind of graph. When a is less than 1, we have that kind of graph. And then look at the relation. 3/2, 2/3, 2, 1/2, 3, 1/3. They're reciprocals. And that relation is visualized as a symmetry. Do you see all those? When a is greater than 1, as you can see, we have repeated multiplication as I move to the right. So all these things increase. Now repeated multiplication by 3 is much bigger, and then repeated multiplication by 2 is the next, and repeated multiplication by 3/2 is the smallest among those three, so that's reflected on the graph. And then to the left is the other way around, repeated division. So green is the smallest, and then followed by red and blue and so on. Now if you look at this, it's precisely the opposite because we are having reciprocals. So repeated multiplication by 2/3, 1/2, and 1/3 are actually repeated division by 3/2, 2, and 3 respectively, and vice versa there. So when a is greater than 1, when a is greater than 0 but less than 1, we have these kind of graphs, and they're associated by symmetry through reciprocals. Here's a grand summary. The domain is negative infinity to positive infinity, clear. Range 0 to positive infinity. Never 0 because we are multiplying or dividing by positive number repeatedly. We'll never hit 0 precisely. So all these here and there, those are asymptotes that get closer and closer and closer to y equal to 0, but never actually hit the x-axis. And then y-intercept, a to the 0 power is 1. As you can see, they all go to the same point. Couple more. When a is greater than 1, we have this kind of asymptotic behavior. To the right, to the infinity and up. To the left, going down to 0. And here, the opposite. To the right, going down to 0. To the left, going infinity up. So remember all these properties. The grand summary. That's all there is for general exponential functions. One more. Here, a is greater than 1. Here, a is greater than 0 but less than 1. But what if a is equal to 1? In that case, we don't have anything actually. We have 1 to x power. It's just constantly 1, so I'm going to get a horizontal line. So that's not very interesting. So in general, we consider only these. A is greater than 1. A is greater than 0 but less than 1. Common properties, and then their unique properties. Again, here's a grand summary of everything. Okay, so much for exponential functions for various different a values.